Hello, JSConf. Way. All right. I am Rik Arends. I have been the CTO and founder of Cloud9 IDE. And I have, in the last 2 years, thrown myself at the GPU and using that thing for UIs and for doing interesting things. And the solution that I have arrived at is called OneJS, and I want to talk to you about that today. How many people here are graphics nerds, and how many here are language nerds? So graphics nerds, language nerds. Good, language nerds are good. If you're making a programming language, language nerds are good. So OneJS. Why? Very simple reason. The GPU has vast creative powers. The programming language that can run on the GPU can determine the color of a pixel with a program, not with CSS background color or a background image, with an actual program. And what that means is that there is an enormous amount of creative possibility that is enabled by the use of programs on the GPU. The only problem is, it is really hard to do right now. There's like a huge air gap between your UI programming environment, like JavaScript, and the programming environment on the GPU, which is GLSL. GLSL is a C-like programming language that came out of Pixar, kind of, sort of. But it's actually kind of a pretty language. It's pretty much just like JavaScript if you take out the objects and you add, instead of numbers, you can do vectors. So you can do A plus B, and A is a vector, and B is a vector, and the result is a vector, where every component is added in parallel, like SIMD. And GPUs are everywhere nowadays. Everybody here is walking around with a GPU in their phone that's more powerful than anything we had on PC a decade ago. So here's my presentation running on the iPad, and it's 60 frames a second on the web. It's really, really nice that we have this kind of GPU power available in our mobile devices. It's not everywhere yet. WebGL is still kind of shitty on Android, actually really shitty on Android, but it's hopefully going to get there someday when they fix the GPU reset bug. But the main problem is that GL and GPUs are really, really hard. They're very difficult and very, very elaborate to make them do things. I'm just scrolling a bit of WebGL API here. It's incredibly chatty. You have to do a lot of setup to get the GPU to do something. So what is the essence of the GPU? How does this thing work? Well, you have to look at it in a way that you can give it a program, a bit of code that is computing pixel colors, for instance, and you feed it data and variables. And the variables are referenced in the program, and the data streams through the program in parallel and is then outputted to pixels. I'm not going to go in deep in the WebGL explanation. Steve Wittens has brilliant demos that if you want to understand how that stuff works, go look at that. I want to focus on how to remove all this cruft between the programmer and the GPU. So one of the things the GPU can do is massive parallelization. This is something that is very easy to do in OneJS. By the way, this presentation is running in OneJS because doing a talk about graphics without using your own graphics engine is kind of lame. So the cool thing about the GPU is that you can feed it data and have these little programs do your styling for you. So essentially, you parameterize the data, and then have the little programs on the GPU do style switches, do style changes. In this case, I made a very simple blob of vertex data, which are the little triangles that go into the GPU. And on every one of those triangles is a letter, is a character of a font. And in that big blob of data, I encode the XY coordinate of, in this case, the word. The word color is compute. And that means that this whole thing is taking like 0.2 milliseconds of draw time in JavaScript and is run entirely on your GPU. There's pretty much nothing going on in JavaScript. This parameterization of styling onto the GPU, I think, is going to be very, very important, and it's going to find, hopefully, a new way to style things on the web that CSS has so sorely lacked. So the parallelism idea, or that this picture is trying to illustrate, is that you have to imagine every pixel as having a function call that computes the color of that pixel. In this case, that function call takes some arguments, an x and a y coordinate, and an animation parameter t, and it decides the color of the text, or the color of the pixel. It's the same concept. So, we all love Brett Victor talks. Who loves Brett Victor talks? Woo! That guy's awesome. But he also had an interesting point about first principles. It was a bit puzzling to me, like first principles, what are those things? But this time around, I tried to find my first principles of what I'm trying to build. And one of the core concepts that I tried to put into OneJS is programmable beyond configurable. Programmable is better than configurable. We all know the declarative space where everything you want needs some implementation from an engine designer, right? Oh, we want another parameter to do something in the engine. If you do it declaratively, then those declarations have to be executed by an engine that somebody has to build. You know, we all know the CSS spec stuff where everything is configurable. But configurability is an enormous limiting factor on the creative potential of what we can do with computers. But this concept, I usually apply it like this. If you find yourself making something configurable, consider making it programmable. So instead of making an API, make a compiler, right? Instead of having a flag, use an expression. At very least an expression and better general function execution. And I try to put this in the details of OneJS. Another one is that style and behavior are irreducible. And by this I mean, if I am encoding a red rectangle, I have to say it's red, and I have to say it's a rectangle. I cannot make a red rectangle out of any less data than those two statements, red rectangle. For buttons, it's the same thing. If I make a button, everybody here has probably made a button in HTML where you go on click, you know, capture the mouse, move your mouse out of the rectangle, mouse up. Oh, that's not a click event, right? That logic is irreducible. If you're trying to implement a button, the logic that manages how you click on it with the mouse is completely irreducible. So the only way to make UI more compact in our expressibility, in the powers of expression, is by composition. Make composition the core aspect. Programmability, composition, because style and behavior are irreducible. So there's no pipe dreams about, oh, let's make the grand unified UI kit. No, that's never going to happen, because somebody's going to want this slider to do something that you didn't program into it. So declarative is always going to break down. And this is something new that has arrived with the GPU. Inefficiency is okay when it's parallel. Because many of you might think, oh, the GPU is so fast. Well, actually, it's not fast, it's parallel, which means that it can run thousands of little programs that run relatively slowly, but you can still get a vast result out of that you wouldn't be able to do if it's a serial language. Because JavaScript has pretty much been a serial language. So we're all accustomed to, oh, for loops are expensive. Well, if you do it in parallel, you can do actually quite a lot of things. So, what to change? How am I going to attack this problem? So if you want to make the GPU programmable in a way that is more accessible from within another programming environment, because we're not doing declarative structures, we're doing programming environments and compilers. We have to fuse GLSL into JavaScript as far as we can, right? GLSL is a C-like language with strict typing, so you have a for vector, and you have a float, and you have an int, and you have an array of this, an array of that. And JavaScript actually syntactically is fairly close to how what GLSL looks like in terms of C. So what I tried to do was fuse these languages at the hip, probably. But fuse them in a way that you can leverage the same syntax, whether you're writing a shader or whether you're writing something that runs in JavaScript. So, by the way, these are syntax shaders, because syntax highlighting is kind of lame. Which means that I actually throw the AST onto the GPU, and you can write little fragments that style your code. I mean, I wrote a code editor thing with my previous company, and this was just like, you want this, right? I don't know why you want this, but it's awesome. So it's not about why, it's about the potential of exploration that you can do. If I can make an error jitter in my line of code, I can add something that is useful. This is not useful, but this looks pretty. So OneJS is JavaScript. I really tried not to break JavaScript, because that's kind of annoying, because then I have to explain a million times why I did something. So I tried not to break it, but I also tried, because it's a transcompiler, I tried to fix some of the problems that are in JavaScript. And one of the things is I finally got rid of semicolons. It's very important. It's visual noise, and I don't like visual noise. But what you have to do to get rid of semicolons is just make it new line sensitive when it reads parentheses or square brackets on the next line. That's all you need to do. If you make it new line sensitive at that point, then you can just get rid of semicolons. Because everybody who's like, no, semicolons is there for a reason, because it blows your foot off if you do this incorrectly. Like, oh, now it's a call all of a sudden. Oh, shit. Right? It blows your foot off. So everybody who's learned that is like, no, we do semicolons. Well, if you can fix that, it's no problem. And I tried to take the ECMAScript 6 spec and 7 and all the ideas that I could find in CoffeeScript and all these other languages, Julia and Lisp, and I tried to fuse it down into something that wouldn't break JavaScript, but would still add the stuff that I needed. Because if you're fusing two execution domains, there is something that is very useful about symbolic expressions. We'll get to that next, but I'll first show you the class, because classes are another very important aspect of the language. Because of the composability, if you have a button and you want to specialize it to do something different, you need to be able to inherit a class and just change one parameter, because that's the most compressed representation of that idea. A button that's a different color. Okay, well, we'll take this button and we'll change the color, right? That's a sort of like a compression algorithm in your expression of code. So classes are super important. I took the ECMAScript 6 thing, except I changed one thing. They're not functions anymore, because I hate .prototype. Have you ever tried to explain .prototype to anybody? Nobody gets it. It's horrible. So I just removed .prototype. My classes are just objects, and I don't have a new operator. I have .new. It's very simple, just because I've tried to explain it so many times, and it's just not going to work for me. Doesn't mean it's not compatible with JavaScript, because it's a superset largely, except if you like to do function calls with parentheses on the next line, then that's your problem. So the interesting part is we have structs and vectors now in this implementation, and we have symbolic expressions. Symbolic expressions are an idea from Lisp, where you do quote, and then you write something in code that looks like code, but it's actually an AST node in the language. So here on the right, you see x is y plus 1, but with a colon in front of it. And the colon is the quote operator. The colon eats the whole expression to the right and turns it into an AST node. And this is really, really, really useful, because now you can start to treat expressions as usable objects in your language. And here's an example of how you draw a triangle. This is not a library that abstracts away what you do. These are the actual data, the vertex shader and the pixel shader that this thing needs to draw this rectangle. There's no matrix stack, there's no nothing. This just is the essence of what the GPU needs to do to draw a triangle. So you can make a vec2 array. This is the syntax of GLSL, how to do arrays, so you can use that in JavaScript. This compiles to a float32 array expansion. So you're really in JavaScript here. I could do a console log in the middle. You know, this is just JavaScript, except it has a few little syntax tweaks. Another one of the syntax tweaks is that is the identifier curly syntax, because I always get very annoyed when I have to express tree structures in a sort of a computable way, that I have to go to JSON or that I have to go to XML, which is horrible, because the language should have a construct that is sort of modifiable to express these tree structures in a way that you can mix it with your language, like a templating structure. I could put a for loop in front of this draw, and it would do it 10 times. So this identifier curly syntax is actually a call. It does object.call, and the curlies are a function. So this just says device.call, blah, 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 wrap with function. That's what it expands to. And it passes in the this, because that is another important thing. OneJS does not have globals. It just slaps this dot in front of anything that would be a global, which means that you can access properties on your object without using this dot, which also makes your code much less wide. So here we have a triangle. And you can see the mesh with the empty brackets, and that actually pulls in the data from the JavaScript space. So I don't have to write attributes or uniforms and all that shit that GLSL does. It's generated for you by looking at what you're using in the shader. It's very simple. Compilers do this all the time. It's just something that needed to be done. So we have device and we have draw, and draw is just a draw call. But if we can inherit from device and make a scene, and we can inherit from draw and make a layer, we can start using the composability to build actual scene graphs. And I know this is terribly ugly because a week ago it did nothing. But this is a very simple example of how you do nested rectangles with matrices, right? So scene graphs work in a way that you have a rectangle that has a matrix, and then something inside it that has a matrix, and these matrices are multiplied together to get the relative offset. That's how the CSS transforms work. That's how the browser does it. That's how you do 2D nested transforms, is by concatenating the matrices. Scene and layer are nothing but a simple class that inherits from device and draw that just implements that multiplication of a matrix. And you can parameterize that matrix with WH and SX. I could call it top, bottom, left, right, and scale X and all that kind of things. I like them short. But anybody could just change that and make a long name for it. And here you can see, instead of background image, you actually just make a texture fetch. And you do background.sample at a certain coordinate. So this rectangle can be parameterized in any way. I can twirl it, flip it, do anything with this code. It's programmable. The styling here is programmable. And the styling actually comes from your class model. So that also means I can do inheritance. I can do CSS-like style classes that are just applied, that just apply these properties. Because shaders are now composable. I can reference an object. I can reference another function on my class. Essentially, shaders have been fused with the class model. I have to hurry up. So interactivity, this is really lame, but it shows you a very important aspect of changing stuff dynamically. So on mouse left down, I changed the symbolic expression of X to mouse X and Y, so I lock it to the mouse. Essentially, the compiler goes, oh, you've changed an expression. Well, let's recompile your draw function and send it to the renderer, and then the renderer does the stuff with the mouse coordinates. So I've essentially told the renderer to data bind. This is expression data binding in the renderer by using a compiler. And it's really cool. You can change any part of your shader functions and variables interactively. I'm still working on the animation system and all that, but we'll get to that later. So these slides are written using a class DSL. Because you have the nesting curly identifier syntax, you can implement a DSL by making a bunch of nested classes, right? You can do class deck, and then a slide is in a deck. This just means that I can only instantiate a slide because it's only known on the class deck. So if I don't put the slide thing in deck, it's just going to say undefined. So now I have a domain-specific language that is encoded in a class hierarchy. So I don't need all these really fancy HTML things. I can just make a domain-specific renderer for these slides. These slides are a DOM tree, but a different kind of DOM tree. It's not a DOM tree that renders all their children and I'm hiding layers. No. The DOM tree is having a custom draw command that goes, I'm going to render the current slide and nothing else, and I know the slide ID. So you specialize the draw function in your call to the DOM. Instead of this being C++ parameterized, it's a programmable render engine that has per node draw calls that you can just change. So the stuff is not ready for use at all. 3 months ago, I was like, yeah, let's do JSConf because it's a nice deadline if you're building compilers and it's to get somewhere. It's really far to hello world when you start with the language. But I still need to refactor. This is a type inferencing compiler. It's kind of my first type inferencing compiler, so I need some refactoring time on this thing. It's actually multi-threaded, so the code that you saw runs in a worker, and the compiler sends the draw calls, the draw code to the main thread, which is really nice because I don't get minimal garbage collection hiccups in my renderer, because all your user stuff that's doing data generation for data visualization or whatever it's doing is not in the render thread. It's perfectly fine in a worker. It's fairly large. It's 130K over the wire because I'm compiling everything in the browser always, and I'm using browser-based local storage to cache the output, which is really nice because I don't like server-based compilation solutions because it limits the composability of your programming construct if you have to pre-compile everything. So it always compiles in the browser, and it's actually really fast. This whole slide thing takes about 450 milliseconds to parse and compile the whole thing, which is pretty okay for probably like 10 or 15,000 lines of code in JavaScript. And if it's cached, it actually starts up much quicker. So iOS is great. I mean, I was like, yeah, WebGL, yeah, bam, and it works. Android is WebGL, and it doesn't work. So the state of WebGL is not that great for mobile yet. I mean, this is great that it works, but on Android, it's not. You have to manually enable it in Chrome, otherwise you can freeze the whole operating system essentially, and that's why it's disabled. So it makes sense that it's disabled, but it's so this is a future-facing technology. This is not something you want to use for a corporate client anytime soon. So the future is constraint layouts. Cassowary is in here imported, and I have it running. And because I have the compiler, you can just write a constraint straight in your code block like this, and it can run the solver on the scene graph. So that's coming. This is all not responsive and has no layout engine because I haven't gotten to that point yet. But I mean, I got away with it because I have essentially expression layouts, so you can do parent width -100, so position something from the right. It doesn't actually have a layout engine, but it will. And I'm going to build a live code editor in this thing itself, because this is, of course, a great way to build a code editor if you can do this kind of text stuff. But also the reason is that I need to bolt the editor onto the AST directly, otherwise the editor is going to be this dumb thing that looks at regular expressions, which is not where you want to be with a code editor. You want to have the full AST, and you want to be able to operate on the AST. So the AST needs to reserialize into proper code, which is what I'm going to work on next. And it needs to work on this thing, the Oculus at 75 Hertz. So I'm really hoping the browser guys can get that done, but I'm actually fearing it might not happen. So the cool thing about this is that it has almost no API exposure, so I can run it in Node just as well as I can run it in the browser. And I'm going to make a prototype of a new Cloud9 UI, because I think it should be quite easily doable. It's on GitHub on OneJS/OneJS. You can look at it and not complain about it, because you can look at it and do stuff with it if you want, but it's not something that I'm throwing out in a supported way, because I'm in the middle of bolting a type inferencing compiler into a code editor, and I need my brain time for that instead of support everything. Yet, because I believe that if I have that editor, support is going to be a lot easier. This actually runs on hello.onejs.io. You can open it up and blow your battery power. Because it's expensive. If you keep that's why you need to stop animating this stuff, right? This is great if you want to burn through your battery, but you need proper dirty regions and not animate everything all the time. This is, by the way, how you can just throw your render scene to Winamp kind of visualizations in 5 minutes, because the composability is super easy. And a good friend of mine, just before I went to JSConf was actually like, you know what? Let's put fractals on the outline of your fonts. And I was like, dude, really? I don't know, it's not useful, but it's so fucking pretty. Right? So that was time better than I hoped. I'm done. Thank you.